Here are solutions to homework set number 8 for ECE 463-663 Modern Control. In this homework set, we're looking at full order observers. Now the goal is eventually want to get to the point where just measuring position and angle, I can estimate all four states, use full state feedback, and get the system to stabilize. Basically go from one point to another, keeping it balanced. So the question is how you do that. So starting out, we've got to come up with the dynamics for the system. That was given in homework set number 4. These are the linearized dynamics. Come up with a stabilizing feedback control law. And again, for observers, as far as they're concerned, they don't really care how you come up with U, just whatever you do to the plant, do the same thing to the observer. So let's just use full state feedback minus kx times x plus kr times r to make the DC gain 1. Come up with the feedback control law in that form. The first part is given the requirements, translate that to pole locations. So a dominant pole with a 2% settling time of 8 seconds means the real part is minus 0.5, 5% overshoot, so that's the complex part, J.52. So place the dominant poles right here. This is a fourth order system, so I have 4 poles to place. These are the dominant 2 poles. The other 2 kind of go anywhere you want. So using pole placement, input the A matrix, B matrix, C doesn't matter. Place the poles where I want, and the other 2 arbitrarily I stick at minus 2, minus 3. Do that and you get a set of feedback gains. Define KR, make the DC gain 1. So here's the DC gain if KR equals 1. It's wrong. Adjust it to make the DC gain 1. So here's KR, here's KX. There's my control law. For the linear system, I can check the step response. Here's the closed loop A matrix, B matrix, C just looks at position, and there's the D matrix. Take the step response, and everything looks fine. DC gains 1, settling time 8 seconds-ish, 5% overshoot. Okay, all looks good. Part 2, design a full order observer. Now this is the separation principle. With the observers, you can put the poles anywhere you want. It does not matter where the feedback control law poles are. The 2 don't affect each other. So make the observer 2 to 5 times faster. I made it 2 times faster. So here's the dominant pole, twice as fast. Other 2 poles out of harm's way somewhere. And here's H. So 2 is pretty straightforward. The next problem, because we're missing problem 3. Oh, this is 3. Using the actual states, check the plant and the observer when the observer initial condition is the same as the plant and slightly different. So in that case, I'll have the system in brown. This doesn't exist. Want to express this in state space form. So here's where Kx goes. I'm feeding back the actual states. And this is X. This is the state estimator or observer. This is the A minus HC goes down here. Here's BKR. Whatever you do to the plant, do the same thing to the observer. Check this step response. If I do that in MATLAB, form the augmented system. Again, this is upward triangular. So here's your A minus BKX, A minus HC. Pretty clear the 2 poles don't affect each other. Checking just to make sure I did it right, it's stable. Plot the step response when the initial condition is slightly different and it gets kind of squirrely. That's because it takes a little bit of time for the observer to converge. While the converger is wrong, you're feeding the wrong input and you get kind of a squirrely output. Eventually it does settle out though. If I make the initial condition the same, it'll look just like problem number 1. Next, the real problem number 4. Change it so that you're measuring the estimated states rather than the actual states. In that case, the BKX goes from the first column over to the second column. So here's my BKX comes over here. That's what you really want. If I knew the states, I'd use them. The whole reason for using an observer is some of the states I don't measure. So if I check that, here's the augmented system. Poles are the same. Plot the step response of the augmented system. and it's really squirrely. That's because the observer states are wrong initially. Feeding back bad gains gives you bad responses. If I make the initial condition 0, then the plant with the observer looks just like problem number 1. Okay, so now that that all works, let's try the nonlinear system. So going over to MATLAB, what this does is here's the initial states for the plant, my feedback control law that I calculated in problem number 1, my full order observer, and here I'm going to put the poles, well, I'm going to adjust these around. Try -1 plus j, -1 minus j, and somewhere else. There's the observer poles, just using position. Let's try that. And initially, I'm going to feed back the actual states and see if the observer can track it. So if I try that, the red one is the plant, the pink one's the observer, and eventually the observer tracks. Okay, that looks good. So now, let's feed back the estimated states. Change this line of code right here. So here's my feedback control law. Updates the plant dynamics. Here's the full order observer. Integrate the plant, integrate the observer. Plot the step responses, repeat. Using the observer states, and it's unstable. Okay, so let's tighten up the observer a little bit. Let's make the observer a little bit faster. See if higher gains makes it work better. Yeah, it looks like I actually made it worse. Okay, so let's make this 0. If the two start out dead on, does it track? And no. So in the solutions, a lot of people are able to get this to work, and apparently you're better than I am. I'm having a hard time getting this to stabilize. Part of the problem is I'm not using angle. On paper, I can tell you what the angle is just by measuring position. That's kind of counterintuitive, but the math says you can do it. The simulation says it ain't easy. So let's change the C matrix. Suppose I measure position plus angle. Now the units are weird. I've got meters plus radians, but the math doesn't care. There's just numbers. If I take into account angle measurements, it's maybe a little bit better. Let's make that a 10. That's looking better. So at least when I run it, I need to use the angle measurement. The problem we have with pole placement is I can only handle a single input. So I don't know what to do if C is a 2x4 matrix. It needs to be a 1x1, or it needs to be a 1x4 matrix. So this number could be pretty much anything you want. As long as the measuring position is observable. The second one adds information. It's the angle. And whether you add 10, subtract 10, doesn't really matter. Whatever you use, it calculates the feedback gain h. And with that, I can estimate the states. A little weird. If I add a little bit of disturbance to it, see what that does. So 0.01 it can handle. If I have too much of an error in the initial estimate of the plant, let's try 2. I can still handle that. Let's try 5. But if this gets too large, the transient gets too wild, and once the angle goes past 45 degrees, it falls. Yeah, so there it kind of struggled. Caught itself, though. But anyway, I'm able to stabilize the Cartan pendulum system using only position and angle measurement. And to do that, I use a full order observer. So that is homework set number 8 for modern control.